Well, hello, everybody, and welcome to our tour of the universe. My name is Jackie. I'm the manager of planetarium programs here at the California Academy of Sciences. Now, we are going to be taking a tour of our universe today, and it's a little bit different than maybe some of the shows you've seen at the Academy itself. This program is run by a software called OpenSpace, which is an open source planetarium software to travel to the edge of the visible universe and back home. I promise I won't leave you out in space. But today we are actually starting our tour relatively close to home, just a few hundred miles above the Earth's surface at the International Space Station. And the ISS, well, that's how we abbreviate it for the International Space Station, is as far as humans do travel nowadays into space. We can fit about 6 astronauts on it at any one time, and it is the largest thing that we have built in space so far as humans. It's about the size of an American football field, or I like to say the Academy of Sciences. So if you've actually walked from one side of our building to the other, you have actually walked the length of the International Space Station. Now today we are going to go much further away from our planet. We're going to see how far our human influence has gone. We'll see how far human communications have gone. We'll also see how far our spacecrafts have gone. But in the meantime, we can actually see the ISS as we're pulling away from our planet. It looks like it's plunging towards planet Earth, but that is just because we are zooming away and it's becoming smaller and smaller. Now, it takes the International Space Station about 90 minutes to travel around our planet just once. So I'm going to go ahead and bring up the path of the ISS as we zoom on out from our planet Earth. And in fact, you can see the ISS pass overhead at night. All you need to do is look up online to see exactly what time is going to pass over your area, and you'll be looking for something that looks like a pretty bright star, but moving very quickly across our planet. Now, before we actually get too far away from planet Earth, I'd actually like to go a little bit closer to home and talk about something that is more recent in the news. We're heading to Chile to see the location of the Vera Rubin telescope. Now, as we zoom on in, you'll start to notice that get a little bit more clarity. And we're actually going to a mountain called Sierra Pochon, where the Vera Rubin telescope has been built and finally released its very first images on Monday. Now, Chile is one of the best places to be able to explore our universe from ground. And the reason is because it is a desert. So there's very little water in the atmosphere. But also, these mountains are very high. So we have little atmosphere we have to actually look through. And so because of that, we get beautiful images. This is an image of the actual telescope itself. And it's one of the largest telescopes we have built. It's 8.4 meters across. And the Vera Rubin Observatory will be looking at the southern sky for 10 years. It's going to cover the entire sky every few nights, creating an ultra wide, ultra high definition time lapse record of the southern sky. It's going to be the largest astronomical movie of all time. Now, because of this unique ability, it's going to bring the night sky to life, yielding the treasure troves of discoveries, asteroids and comets, pulsating stars, and supernovae as well. Now, I did tease that we got the very first images from this telescope, and this was the very first one that they showed. This is taken in the Virgo cluster, which we'll be able to see a little bit later today in our tour. And this image is actually only a tenth of what the full image is. If you like to explore the full image, you can go online in the link provided in our chat box and explore this image even closer. But this is spectacular from a ground-based telescope. Normally, we think of this type of image coming from our observatories that are in space, like Hubble and JWST. But I am very excited to be able to explore our universe even better with this brand new telescope that just came online. All right. Well, that's enough gushing of the types of beautiful images that we've gotten just this week. We're going to go ahead and head back to our tour. And to do this, we're going to go ahead and visit our closest natural neighbor, and that is the moon. Now, as we zoom on to the moon, we're going to see the dark side, which is the side that's facing planet Earth right now. And you'll start to see that there's this line coming from the moon. That is an artificial line that I've placed up to show the path of the moon. And you'll see some of these lines continue as we tour our universe. Now, the moon is our closest natural neighbor, and it is as far as humans have traveled out into space. The astronauts of the Apollo mission came out here in the 1960s, and it took them about 4 days to get to the moon. Now, even though the moon is our closest natural neighbor, it doesn't mean it's close in human terms. The moon is 250,000 miles away from our planet. And as we get farther and farther out today, we are going to be going distances of millions, billions, and sometimes even trillions of miles. And when we get to this far out distances, it doesn't make sense for us to use miles or kilometers as a measurement of distance anymore. So from here on out, I'm going to use a different yardstick, so to speak. The speed of light, the fastest thing that we know of. Now, if we were actually traveling the speed of light, and which is about 200,000 miles per second, it would take us 1.5 seconds to get to the moon. So we say that the moon is 1.5 light seconds away from us, or our planet. But let's go ahead and zoom on in just a little bit closer to the surface of the moon. Now, the moon gives an illusion that we've been hit by asteroids or that it's been hit by asteroids or comets a little bit more than planet Earth. Now remember, Earth is actually a much bigger target, so we get our fair share of impacts. It's just that the moon has basically zero atmosphere and no weathering and no erosion. There's also no plate tectonics that are moving around, so nothing is erased once it actually hits the surface of the moon. Now you've noticed that we've actually have some great detail of the moon and also Earth so far, and that's because OpenSpace is able to bring data that is constantly being updated. And so everything you're seeing today is based off of where everything is as of yesterday, as well as all the surfaces and information is based off of surveys and data from NASA, ESA, which is the European Space Agency, as well as other agencies as well. But this far out, we can actually see the path of the moon around our planet Earth. Now, it takes about the moon about a month to travel around our planet, or I like to call it a month because it's not quite a full month. It's actually 29.5 days. Now, let's go ahead and continue our journey because we still have quite a bit to go. And I'll start to bring up the paths of the other planets in our solar system. So we see the path of Earth as we zoom on out. And we can also see the sun in the center. Now, if we were traveling the speed of light, which it would take us 8.5 minutes to get from the sun to Earth. So we say that the sun is about 8.5 light minutes away from us. And we can see those planets again, starting from the center. We have our sun, then we have the rocky planets, what we call our inner solar system, which have Mercury, Venus, Earth, and Mars. And further out, we have the gas giants, Jupiter and Saturn. And even further out, we would have the icy giants, Uranus and Neptune. Now, it looks like there's a pretty sizable gap in between Mars and Jupiter, and there's nothing there. In fact, this is where our main asteroid belt is. So all these little dots that are green are individual asteroids. In fact, they're not all the asteroids in the asteroid belt. If I brought up every single point for every single asteroid that we know of, my computer would actually crash. This is about 70% of the asteroids we know of that's visualized. And what's really cool about Vera Rubin, yes, I have to talk about it one more time, is that not only is it going to be able to tell us these beautiful images of distant places like the Virgo cluster, but also it's because it's a time lapse and we take images constantly and quickly, we're able to capture images of asteroids in our solar system. So we're finally going to be able to have a catalog of our asteroids and the paths and maybe discover some new asteroids or near Earth asteroids that we should be concerned about. Okay, I'll stop gushing again. Let's go ahead and go back to our program. So not only do we have our asteroid belt, but we also have objects in the outer parts of our solar system, what we call trans-Neptunian objects, or TNOs. And these are objects that are out here in the outer parts of our solar system, way past Pluto. And most of them are icy and rocky. But there are some quite large objects out here, what we call our smaller type objects, not planets, but our dwarf planets. And so we consider Pluto a dwarf planet, but we also consider another object in the asteroid belt, Ceres, a dwarf planet as well. Okay, well, I'm actually going to go ahead and turn off our asteroid belt and our trans-Neptunian objects because they tend to slow down my software. But let's go ahead and continue our journey. And while we're out here in the outer parts of our solar system, we can go ahead and bring up Pluto's orbit to give us a sense of how far we have traveled so far. If we were able to travel from one side of Pluto's orbit to the other, it would take us 10 hours traveling the speed of light. So it's about 10 light hours across. And also, let's recap. So the sun is 8.5 light minutes away, and the moon is 1.5 light seconds away. But even way out here, we can actually check in our human influence. We can see how far our spacecrafts have gone. I'm going to start to bring up the paths of some of the fastest and farthest spacecrafts we have sent out into space. We have Voyager 1 and Voyager 2, Pioneer 10 and 11 that were sent out in the 1970s, and more recently, the New Horizons spacecraft, which was sent out by NASA, went out to Pluto back in 2015. Now, as I mentioned, these are the fastest and farthest spacecrafts that we have sent out into space, but none of them have traveled as far as light has traveled in one light day. But let's go ahead and continue our journey. We still have quite a bit of space to explore. And now we're going to be going distances of light years. we are going to be flying past some of the other galaxy or other stars in our galaxy. Now, the closest star to us, well, beyond the sun, is about 4 light years away from us. So it would take us about 4 years to travel there at the speed of light. And even way out here, we can actually check in one more time on human influence. I'm bringing up a grid, these kind of bluish lines that are showing how far our radio waves have gone out into space. Now, when I mean radio waves, remember light is a spectrum and radio waves is actually a type of light. And we've been sending radio waves for quite a long time on our radios, then television signals. And then we also have some other objects that create these radio waves as well. And they escape our planet and they continue to move out. In fact, the first radio signatures that have been able to escape our planet were sent out in the 1930s. So this is about 90 light years away from us in all directions. And out here, we can also check in on how many planets we have found outside of our solar system, what we call exoplanets. We have found thousands of exoplanets so far, and if you look carefully, there are several planets inside that radiosphere. So who knows? Maybe there's somebody listening to Nat King Cole. That'd be pretty neat. Okay, let's continue to zoom on out. And I want you to kind of keep an eye on that radiosphere and see how long it will take for you to maybe lose it or maybe you can keep track of it. And soon we'll start to see the large scale structure of our galaxy, the Milky Way. Now we live in what we call a spiral galaxy, which is made of gas and dust and stars. And all that gas and dust and stars make up part of it. But we can see there are a lot more stars in the center of our galaxy. And if we could see past all that kind of craziness that's the center of our galaxy, we would actually see a giant, massive black hole. All right. Do you still see that radiosphere? Go ahead and point towards it. Well, you're all correct because I have no idea where you're pointing. But I'll use my arrow to point out where it is. It's just kind of over by, it looks like my arrow's showing up a little bit. But if we consider the galaxy a clock, it's kind of around 5 o'clock. We're about 2/3 of the way out from the center of our galaxy. That's how far our human communications have gone, just in our own little backyard. And now we're at distances of thousands of light years. In fact, from one side of our galaxy to the other, it's about 100,000 light years across. So if we wanted to take a round trip from one side to the other and back again, it would take us 200,000 years. But our galaxy is just one of many out here in our universe. Now we have our share of stars. We estimate about 400 billion stars. But every dot we see now is not a star itself, but a galaxy with its own millions and billions and sometimes trillions of stars. And the colors of these galaxies may make it seem like we accidentally spilt some cosmic skittles in our universe. These are not the actual colors of the galaxies. They represent the different surveys that have mapped these galaxies. And as we zoom on out, we can start to see a large-scale structure of our universe. And you may notice a couple of weird things while we're looking at the large-scale structure. There are some clumps and there's some pretty empty spaces, but you might notice there's a lot of big empty space. Now, this isn't because our universe is shaped like a bow tie or a butterfly. That would be pretty cool. This is because of our perspective and how we are viewing our universe. Now, remember when I told you that our galaxy is made of gas and dust and stars? Well, that gas and dust actually blocks our view. So we can't actually see past our own galaxy. So these big, very large empty spaces is because we haven't been able to map the universe there. We're pretty sure that there are galaxies there, but we're not showing you it. You also may notice that it looks like we are the center of the universe. Now, as far as we know, there's actually no center of the universe at all. It's, again, our perspective. We are making the map. If we were to go to any one of these other galaxies, say in the upper right corner or the bottom left corner, and we were taking a look at our planet, it would appear as if we were the center of the universe. As I mentioned, there is no center of the universe as far as we know. It's just our perspective. But let's go ahead and continue our journey. We still have a little bit to go. And we'll start to see some of the farthest and earliest objects in our universe, what we call quasars. That's what these kind of reddish dots are. They show where the bright, very first galaxies are. Now, I do mean earliest because any time that we are looking out into space, we're kind of time traveling in a way. Because it takes the light of those objects to travel so far. By the time it travels all that distance and gets into our telescopes, we're actually seeing how they were in the past, not how they look today. So, for example, when I was looking at, or we were looking at the closest stars to us, that 4 light years away from us, that's how they looked 4 years ago, not how they look today. And we are now seeing the universe as it was billions of years ago. And because of that, there's an edge to everything that we can see. And that edge is now visible. Kind of this splotchy, kind of dark and bright spots. This is what we call the cosmic microwave background, or CMB. Now, if you had a radio telescope and could see the microwave range of light, you would be able to see this everywhere you looked. In fact, the first radio astronomers were pretty confused because they thought it was interference and they were like, what is going on? But soon they realized it was actually something they were seeing out in space. And this is a few 100,000 years after the Big Bang would have happened. So you can think of this as the baby picture of our universe. Since this is the first light that we can see, there's nowhere else we can go. So let's go ahead and head on back as we go home. Now, if we were that far out into space and we were actually flying the speed of light, it would take us 13.5 billion years to get back home. But thankfully, we have the power of our planetarium software, so it should only take us about a minute. And as we zoom on back home, all that we looked at today, all these stars and galaxies in the cosmic microwave background, well, that's not everything in our universe. There's dark energy, this mysterious force that's causing space itself to accelerate as it expands. And there's dark matter, some mysterious substance that doesn't seem to interact with light at all, but we see evidence of it in between and at the edge of galaxies especially. And we call all these things dark energy and dark matter. Well, we're not exactly sure what they are. But we do know that they make up about 96% of our universe. So that means everything that we saw, everything that we can see right now is only 4% of everything out there. And that may make us feel a little bit small, like we're one tiny dot in this homogeneous universe. But I like it to think of it this way. Yes, we're one tiny dot. But look at all that we have found, almost entirely by looking through telescopes. And there's a whole lot more for us to discover and a whole lot more for us to learn. And that's what makes it a wonderful time in human history, that we're not just able to learn about them, but to show them like this, a map of the cosmos in 3 dimensions. And we're only just starting to unravel the true nature of our universe. The rest is up to the next generation of scientists back here on planet Earth. Well, we are home. And so I would like to thank you all for joining us for our tour of the universe. If you'd like to learn more about the Vera Rubin Observatory, again, you can use the link and explore those images. Promise that's the last time I'm going to gush about it. But also, we would love to hear from you on what you thought of our program. Again, this is a open source software that you can download at home. So if you want to fill out a survey letting us know, and you can download the software at www.openspaceproject.com. Thank you, everybody, and I hope you have a great rest of your evening.